Hey guys, I'm Eric,
I'm Rashad. I'm Christian. I'm Angel.
and we are.
Why Wizards?
The problem with UV radiation is that exposure to it is invisible. So you wouldn't know whether or not you've been exposed to it until you see the symptoms of it. So pretty much the symptoms of UV exposure, pretty much you can see it yourself. You can either see that like your skin, you can see like aging of your skin, and then you'll see that little tiny dots like moles in your skin. Some people often say that that's not skin cancer, and other people say that it is. But it's better if you get diagnosed by a doctor just to make sure. And here, this image is an example of how UV radiation often ages your skin. You can see that the left side of this person's skin is also looks, I guess you can say, young, while the other side looks all wrinkled. That is pretty much the exposure to UV radiation that's causing the aging of the person's skin. So our motivation behind this product is to make a product that is able to warn the person of the current UVI conditions around their environment. This is so they could do any preventative measures to avoid any damage to their skin. As you can see here, these are the different types of UV lights. So you can see that the UVA is able to penetrate through the person's skin compared to UVB. That's because the UVA has a much more smaller wavelength compared to UVB. These types of UV lights are responsible for the aging that happens and also the skin cancer that appears on your skin.
Our objective for this project is to measure the UV index using both UVA and UVB light. We'll be providing real-time feedback using LEDs ranging from green, which is safe, yellow, which is moderate, and red, which is dangerous. And with that dangerous reading, we'll also activate a little beep to let the person know that they're in a pretty bad environment right now. And we also want to make this lightweight so the user can put it anywhere with their keys or ideally their backpack so it's easier to carry around or a zipper, just anywhere where you'd usually put a keychain.
Shape and ergonomics. Rounded, rectangular, and closer reduce sharp edges while maintaining flat faces. Flat front surface support organized placement of LEDs, speaker opening, and UV sensor. Front facing layout allows the UV sensor to receive direct obstructed sunlight. The front face layout LEDs indicators placed at the top for quick at a glance visibility. Central speaker opening allows unobstructed audible alerts. Device provides automatic visual and audio feedback without user input. Device provides automatic visual and audio feedback without user input. Layout minimizes user interaction while maximizing awareness. So this is our main design. This is our main sketch. With this main sketch, it allows front-facing UV sensor LED indicators for real-time feedback. Audible alert activates when UV exposure reaches unsafe labels. Rounded rectangular form supports compact wearable use. So the three circles, those are the LEDs, and each LED has a color. Green means safe. Yellow is where it's like okay, but be alert, and red is dangerous. The middle, the dot, a lot of dots, that's where the sound is emitted. And the square, that's where it be for the sensor.
So this is our design matrix. We had to exclude any type of design that had like a pot that involved a pocket. So here we have the first criteria is sun exposure. So you can see here that the zipper attached use has a 5. That's because it's constantly going to be on your backpack, zipper of your backpack or a keychain. Unlike the handheld one, how it's only 3 because usually whenever you use like a handheld device, it's you're always tempted to put it in your pocket, so the readings will pretty much be inaccurate. So now the next criteria is the user effort. So that pretty much means is how much, like as it says, how much effort a person has to use in able to be able to use it. And now let's go to hands-free operation. So for zipper attached use, there's a 5 because uh, people don't really have to attach, no, don't have to interact with it as much. Simply, all you have to do is pretty much attach the device on a zipper of a bag and pretty much just leave it there. the device itself will pretty much do work on itself. Now the next one, for the handheld use, it's a one because the person will have to be interacting in it a lot more compared to the zipper one. So now the next criteria is the consistency to exposure. The attached one has a four because it's constantly going to be exposed to the sun, but the only reason it's a four is because it's going to be like moving a lot. So there might be some moments out there where it won't be getting data as much. And now we go back to the handheld use where it's a three because, as like I said earlier, it's a handheld, so you will be more tempted to put it inside your pockets. So that's why it's a three. So now pretty much the total score is a 19 for the zipper attached use and a 12 for the handheld, which means that we're going with the zipper attached design.
For this project, we use an Arduino Pro Mini to be able to control all these components with the UV sensor that will get the measurements of the light, and a SparkFun serial adapter to be able to code with the Pro Mini. We got a battery just to power everything, the active buzzer alarm to be able to alert the user if the UV gets a little too high. We also got a few cables to connect the battery and the other stuff. It's a metal pinheads to just connect around with the adapter, and the switch to be able to actually turn it on and off so it's not constantly wasting battery. And with that, we come out to a total of around 49.92.
This is the general overview of our wiring, where first starts at the slide switch, which turns the device on or off. This can say battery if it's off. And the battery will go to the Arduino, which is the processing for everything in our project. It will then go to the UV sensor. And what the UV sensor does is that it measures the light levels in the area and outputs a voltage for the amounts that it sees. We can then read that voltage to determine how damaging or how fine the sunlight is. The voltage will then be processed and sent to the LED indicators. And if the voltage is lower, then it will be a green indicator. And if it's higher, it will be red. If it is red, that will mean that you need to be inside for a longer amount of time to prevent longer exposure to UV sun. So this is the general design sketch for our project. To the right here, we have the inside view of our project. This is that same view expanded. We can see the large back is a battery. To the right of that is the processing unit, and the switch is the one to the right of that as well. Below that is a beeper, and that makes sound if this UV light is too damaging. You will also see the UVA, that's the UV sensor. The red section is the charging port, where if the battery runs too low, you can charge it using that. And it's a USB-C cable.
So this is our structural analysis right here. As you can see here, on the sides and top, we applied 20 newtons of force, which is equivalent to 4.5 pounds of force. As you can see, there are minor dents that occur on both the top and side, meaning that our uh, our product can withstand a decent amount of force. So the only way you could break this is if you really actually tried putting like a lot of force into it, if you really wanted to. So as you can see here, this is our technical drawing of our product. Here are 27 holes, which will be the speaker, all at zero point 0.5 millimeters. And now these three holes here pretty much represent the LEDs that we're gonna be using to warm the person. So as we explained, this is going to be the green, yellow, and red. All of them are going to be at 5 millimeters. And now this hole here is where the UV sensor is going to lie. So this is where the UV light will pretty much travel to, and this is where the UV sensor will read. And if we go more to the right, we can see that this is pretty much the charging port right here. So pretty much our enclosure is pretty much what 3 millimeters of thick. So it's very compact for the ordinary person. One of the major challenges we face is the lack of time that we had to come up with a physical prototype. That pretty much caused us to pretty much cram as many ideas as we can just for one design. Another challenge that we had was the availability that we all had. Many of us were busy studying for finals or have some personal stuff together, so many of us couldn't or weren't able to like talk together in groups. Another challenge was the UV sensor itself because the UV sensor seems to be very delicate. So whenever we were trying to code it, like for example, in a room like this, the UV sensor will be giving out, for example, the UV index of 9.5, while in reality, the UV sensor should be giving out a zero since there's like no sunlight, almost to sunlight. So now, one of our future improvements is to actually test them in an actual environment, like a forest, to see what the UV index is around the environment, and then possibly we can work on weatherproofing the device itself, such as making it waterproof, rainproof.
Conclusion: successfully designed a compact, wearable UV monitoring device. Met design goals for real-time visual and audible UV alerts. Validated enclosure strength through CAD and simulation. Future works focus on physical testing and calibration.
And with that, this was our presentation.
Thanks for watching.